This is the third video in a three-part video series discussing area between curves, a topic for Calculus 1 courses. These videos are based on the OpenStax Calculus series, Volume 1, Section 6.1, Area Between Curves. In this third video, the final one in the series, we look at some examples and first to determine whether to integrate with respect to x or with respect to y. We'll see that sometimes it makes no difference whether you go with respect to x or with respect to y, and sometimes one or the other is clearly easier. Let's take a look now at what's on the screen. There are two different formulas that you will need to use in order to integrate with respect to x and with respect to y. The primary difference being that you must solve the equation for y in terms of x in order to use the integral with respect to x. Your limits of integration must match the differential and be x values. If you wish instead to integrate with respect to y, you must instead solve the equation for x so that it is written in terms of the variable y, which you will then use in the interior part of the formula in the integrand. The limits of integration in this case become y variables. Sometimes it does not matter whether you integrate with respect to x or with respect to y. It's just as easy either way. Let's look at an example where that's the case. You'll see here in example 1 that we're to find the area between the curves y equal x squared and y equal the square root of x. I've already produced the graph here from Desmos so that you can see what it looks like. If I were to do it with respect to x, then I would need to draw all of my rectangles in the vertical direction. That means that if I'm looking at them, that I would have a rectangle extending between the two. Notice that as I move across this closed and bounded region, on every vertical rectangle, I would have the square root of x as the upper curve and the parabola as the lower curve. That means that I would only need one integral to integrate with respect to x, since the differential corresponds to the short end of the rectangle, dx. On the other hand, if I choose instead to integrate with respect to y, then my rectangles should be drawn in a horizontal manner. This means that the short end, which represents the differential, would become dy. In this case, we need to look to see which curve is furthest to the right, since we will subtract from it the curve that is furthest to the left. In this case, it is always the parabola that is to the right and the square root function which is to the left. Take a few minutes and pause the video, set up the integrals, and then restart the video to see if your integrals match mine. Whether we intend to integrate with respect to x or y, we will need the points of intersection. While it seems clear that they are 0, 0, and 1, 1 from the graph, you must not rely on the graph. You must use algebra in order to determine the points of intersection. In this case, you can set the two y expressions equal to one another. This leads to x equals x to the fourth power after squaring both sides of the equation. Make sure you do not divide by x, since you will lose one of the points of intersection if you do so. Instead, move the monomial term x to the opposite side so that you can get 0 on one side. Factor out the greatest common factor of x, and then you can factor the binomial, that is x cubed minus 1, as the difference of two cubes. This leads to three factors. The first two give you your points of intersection. The third gives you a complex solution with an imaginary part. So it is not a point of intersection since it does not occur on the real portion of the graph. Now you'll notice that both the x coordinate and the y coordinate are identical. This is not always going to happen, of course, so don't expect this to always be the case. If you set up the two integrals, one with respect to x and one with respect to y, you'll discover when solving the equations for x instead of y, in order to use dy as the differential, that in fact you get precisely the same integrand. This may not always occur either. Don't expect it. In this case, because it does, and because these are both definite integrals, remember that the variable used is a dummy variable and will disappear since our result will be a constant. Thus, it doesn't matter whether we're using x or y. In this case, we'll get 1/3 in either method. Let's take a look at an example where it definitely does make a difference and where one method is much easier than the other. In example 2, we're to find the area of the region bounded by the curves x equal y squared minus 4 and g of x equal to x divided by 3. By looking at this region here, you can see that the only one that is bounded by just those two curves is this region here in between. If we're looking at this, would there be a difference if we integrated with respect to x versus integration with respect to y? Let's take a look at these now. If I draw vertical rectangles, and this means the differential is dx, notice that on the far left, the upper portion of the rectangle touches the upper half of the sideways opening parabola, whereas the bottom touches the bottom half of the sideways opening parabola. Neither part touches the slanted line here in red. On the other side, however, it is different. On the other side, the vertical rectangle, also differential dx, touches the upper half of the sideways parabola on top, but the slanted line on the bottom. That means that if I wish to do this with respect to x, that I must split the integral into two pieces, right there, where the curve on the bottom changes from the lower half of the parabola to the slanted line. Let's now take that portion off and see if it would make a difference if we integrated with respect to y instead. If we are looking with respect to y, then we need to draw horizontally shaped and oriented rectangles. This will make the short end the differential dy. You can see that on the right side, they'll be touching the slanted line, and on the left, they'll be touching the upper part of the parabola. When you go with respect to y, however, it is simply a left-right thing, so it doesn't matter in this case whether it's the upper or the lower half. It is slanted line on the right, parabola on the left. If we're looking now at the next portion, we'll see that again, it is the same two curves on the left and the right. When we reach this portion, notice that it is again the same, and the same here, and the same all the way to the bottom. In other words, we always have the slanted line on the right and the parabola on the left. That means that it would be far simpler to integrate this problem with respect to y. In order to find the points of intersection, you need to be able to either solve for the same variable and set the two expressions equal, or you can use substitution instead. In this case, either is relatively simple. Let's take a moment and see what the points of intersection for this curve must be. The upper curve that we have is the parabola. The parabola is given by the equation x equals y squared minus 4. The slanted line is given by the equation y equals x divided by 3. I can solve the second equation easily for x by multiplying both sides by 3. Then I can equate the two expressions to each other. This leads to y squared minus 4 equal 3y. Remember to get everything on one side of the equation so that you can solve the quadratic equation. This should lead you to write y squared minus 3y minus 4 equals 0. Factoring as the product of two binomials should lead to y minus 4 as a binomial factor times another binomial factor, y plus 1. This gives us two possible values for y, 4 and negative 1. If y is equal to 4, then I can take that value and look up here to find the x value. It'd be easier to use the equation where it's solved for x, but any of these will work. If y is 4, then the x value must be 12. This gives me a point of intersection of 12, 4. When y is negative 1, the x value should be negative 3, which gives me another point of intersection, negative 3, negative 1. Looking back at the graph, I can believe that this one is in fact 12, 4, and this one is in fact negative 3, negative 1. Let's now set up the integral. To do the integral, I need to remember which is on the right, since the right curve is the positive one and the left curve is the negative. When using the differential dy, be sure that you have solved the equations for x, then use the expression on the opposite side in the formula. This gives me the line first, which is 3y, minus the equation for the parabola, which is y squared minus 4. Make sure that you put the y squared minus 4 in parentheses, since you are subtracting the entire thing and not just the first term. That means the negative distributes and will give you negative y squared plus 4. Make sure that when the differential is dy, that you choose the y coordinates to be the limits of integration. We should integrate from negative 1 to 4, not use the x coordinates. This gives me negative 1 to 4. Since this is a relatively simple one, we can go ahead and complete it quickly now. You can go ahead and write below it that you would get 3y minus y squared plus 4 as the integrand. The antiderivative of each term would become 3y squared divided by 2 minus y cubed divided by 3 plus 4y. This must be evaluated between negative 1 and 4. Moving to the next term, then, what we should be able to do is plug in the limits of integration. Plugging in the upper limit of integration, I would have 4 squared minus the quantity negative 1 squared minus the 1/3 coefficient of the second term times 4 cubed minus a negative 1 quantity cubed plus the coefficient of the third term 4 times 4 minus a negative 1. Simplification would lead me to have 3/2 times 16 minus, well, a negative 1 squared is positive 1, so 16 minus 1 would give me 15. In the second term, we will have the negative 1/3 being multiplied by 4 cubed, which is 64. Be very careful with the next part. The minus that's in the middle is from the formula, the upper limit of integration minus the lower. A negative 1 cubed, however, remains negative, so I get a double negative, which becomes addition. This results in a sum of 65. In the last expression, you also have a double negative, and you get 4 plus 1, which is 5. And 5 times 4 will give us 20. In the next step, of course, you need to multiply this out and simplify. Take a moment to see what you get if you do the arithmetic. Hopefully you got 125 divided by 6 after getting the common denominator, which is the mixed number 20 and 5/6. Remember that fractions are preferable whenever the fraction does not terminate. Let's take a look now at example 3. In example 3, we are asked to find the area of the region bounded by two different curves. These curves are given here and are, in fact, both sideways opening parabolas. However, one is opening to the right and the other is opening to the left. We will need to know where the points of intersection are, which is probably where we should start. We can also take a look and now think, would it matter whether I use integration with respect to x or integration with respect to y? If I think about integration with respect to x, I want to visualize drawing rectangles that are vertically oriented so that the differential is dx. If I do this, notice on the left that I have the blue parabola on top and the purple parabola on bottom. On the far right side, however, I have the blue parabola on both top and bottom. That means to integrate with respect to x, I would need to split the space into two regions, here where the curve on the bottom switches from purple to blue. That means that it might be easier to go with respect to y. Let's take a look at that instead. If we do that, we need to draw our rectangles running horizontally so that the short end, the differential, is dy. In this case, it looks like in every situation I will have the blue parabola on the right and the purple parabola on the left, no matter how high or how low in the region I go. That makes integration with respect to the y variable preferable. Let's now set these two equal to each other, since they're both solved for x, and find the points of intersection. You will want to move everything to one side of the equation so that you can solve the quadratic. In this case, I choose to move everything to the left so that my y squared term is positive. Now, let's take a look at what we end up after accomplishing that. This would give me 3y squared plus 3y minus, 18 equals 0. I am looking for where the two intersect, so it doesn't matter if I divide by a common factor. It won't change the solution for the intersection points. Thus, it makes sense to go ahead and divide every term on both sides by the common factor of 3. This will make it easier to factor if indeed it does factor. If it does not mean you're done. It just means switch to the quadratic formula or complete the square. This gives me y squared plus y minus 6 equals 0. I have very kindly chosen mostly ones that do in fact factor. And I will do a similar thing on the exam. This gives us y plus 3 as a binomial factor and y minus 2 as a binomial factor. This gives us two possible y values, y equal -3 and y equal 2. Both of these represent points of intersection between the two curves. That means that I can use either one and find the x value. Let's copy and paste this below so that we can plug it into either one of them. If I put this down below, let's use the one on the left since it is slightly simpler than the one on the right. Plugging this into the one on the left, then, I have x equals -3 quantity squared minus 3 times -3 plus 12. This would give me 9 plus 9 plus 12. 9 plus 9 is 18, and 18 plus 12 would give me 30. This will give me the ordered pair 30, -3. Let's check the graph and see if we believe that. 30, -3 does appear to be this point over here where they intersect. That would be this point right there, 30, -3. Now let's see if we can find the ordered pair for this point where they intersect on the upper region. I'm expecting it to be close to x equal 10 and y equal 2. I'll again use the first equation since it's simpler and since it should work in either equation. This gives me x equal, now we use the y value of 2 to find the second point of intersection. 2 squared minus 3 times 2 plus 12 results in 4 minus 6 plus 12. That would give me negative 2 plus 12, which is 10. Notice that this is exactly what I expected to get, the point 10, 2. Now we need to finally complete our problem by setting up the integral. To do that, I need to know which one's on the left and which one's on the right. Remember that a right opening sideways parabola must have a positive coefficient on y squared, which means it is the purple one. The one that opens to the left, which is the negative direction, has a negative coefficient on y squared, so it's the blue one. In this case, however, when we look at our closed region, it is the blue, the negative, that is on the right. So it should be the negative one minus the positive one. In this case, then, we should set up our integral as follows. We should have the blue one first, which is negative 2y squared minus 6y plus 30. Minus for the formula, then you must put the entire second parabola in the parentheses. But don't forget to distribute that negative. All the signs must change. Remember to use y values for your limits of integration since your differential is dy. We'll take a moment here and allow you to distribute it. If you do this, you can, of course, if you allow enough room, work directly underneath without having to write and rewrite and rewrite. This would give you a plus 3y and a minus 12. Notice that you do have like terms. Negative 2y squared minus y squared will give you a negative 3y squared. This would lead to an integrand of negative 3y squared. Combining the negative 6y and 3y would give negative 3y in the integrand. And combining the positive 30 and minus 12 would give me plus 18 in the integrand. Then I integrate from y equal negative 3 to y equal 2 with respect to y. In this case, I do have a common factor of 3, which I could pull out, but it'd be just as easy to leave it stay and then pull it out when I plug in the limits of integration. That is probably what I would do. Let's now go ahead and find the antiderivatives. This would give me negative 3 y to the third divided by 3. This will result in cancellation of the 3's, but the negative will remain. This will give me a negative y cubed at the next step. For the center part of the integrand, I will integrate using the antiderivative of y squared divided by 2. This will, of course, remain negative 3/2 y squared. The final term from the integrand becomes plus 18y, which also will not change. All of these need to be integrated between the limits of integration, which are negative 3 to 2. In the next step, we will want to plug in these limits of integration in order to evaluate the definite integral. This is where you would remove the coefficient and leave it to be done after plugging in the limits of integration. I would have 2 cubed minus for the formula, negative 3 for the lower limit cubed, minus 3/2 for the coefficient, times the quantity 2 squared for the upper limit minus the quantity negative 3 squared for the lower limit, plus 18 as the constant factor times 2 for the upper limit, minus for the formula, -3 for the lower limit. Once I do the arithmetic, this should lead me to have 8 minus a -27, since a negative cubed remains negative. A double negative makes it plus, and that will give me 35, but the negative on the outside results in a -35. For the second term, I get a 4 minus, but in this case, the -3 is being squared, so I get 4 minus 9. That will give me a -5. The -5 times the -3/2 will result in a positive 15 divided by 2. In the last term, the double negative in the center gives me a positive, which results in 5. 18 times 5 gives me 90. If I subtract the 35 from the 90, I should end up with 55. If I take the 55 then and add on the 15/2, I should be able to come up with the final answer. Since 55 is 110, this would give me 125 divided by 2, which could also, of course, be written as 62.5. That would be the final value for this example. Let's now move on to the next example. This is the final example for this video, and it is a more complicated one. In this case, we have a sideways cubic and a sideways parabola. You'll notice that there's more than one closed and bounded region between the two. If I look at these two, I can see right away that going with respect to x would result in having to split up at least this larger region here. How about going with respect to y? If I go with respect to y, I would instead have the blue on the right and the purple on the left everywhere in the upper region. However, in the lower region, notice they swap locations. This means I do have to split it up, but while I would have to split it up, it would not be as bad as it would be if I integrated with respect to x. It would also be far easier to leave them in their current format, where it is solved for x, which means the differential would need to be dy, than to try to take this cubic and solve for y. It might not at this point even be possible for us to do that. This means that we will need to integrate with respect to y. First, we need to find the points of intersection. To find the points of intersection, take the expressions for each representation of x and set them equal to each other. Let's do that part now. Looking for the points of intersection, I will have the following. I need to write that y cubed minus 4y squared plus 3y is equal to y squared minus y. That gives me this equation. We again need to move everything to one side of the equation, and hopefully we will be able to factor it. If we are not able to factor it, we may have to resort to graphing in order to figure it out, but let's see if we can factor. Moving everything to the left will result in the following. I will end up with subtracting the y squared and adding the y to both sides. This will lead to having a common factor on the left, which means that I should be able to factor it completely, since after taking out the common factor of y, it will be quadratic in nature. This gives me y cubed minus 5y squared plus 4y equal to 0. Be sure that you do not divide by y, since you will lose one of the points of intersection if you do that. This gives me y squared minus 5y plus 4 as the quadratic factor. If it didn't factor, then I would have to use the quadratic formula, but fortunately it does. This gives me y minus 4 times y minus 1. This gives me 3 different y values, 0, 4, and 1. I can use any of the equations that were used to produce it in order to find the x value. However, the simplest would be x equals y squared minus y. Let's go ahead and write that to the side so that we can remember what it is. Now I will solve for x. In the first one, well, obviously, if I square 0 and subtract 0, I still have 0. So our first point of intersection is the origin. Looking back at the graph above, we can see that yes, the origin is a point where these two do coincide. Let's find the next one. This says when y is 4, they should match. To find the x-coordinate, I need to square the 4 and subtract 4. That gives me 12, or the ordered pair 12, 4. Looking back up at the graph, it does appear that out here at 12, 4, I do have a point of intersection. Now let's find the third and final point of intersection. When y equals 1, x should be equal to 1 squared minus 1, which is 0. If I have that, this would be the ordered pair of 0, 1. This is above the origin. Let's look back at the graph, and in fact, we do see that there are 2 points of intersection on the y-axis, one at the origin and the other at 0, 1. Now we need to remember what order to set up the integral in. Remember that the cubic is purple and the parabola is in blue. In the upper region, we will have on the right side the parabola and on the left side the cubic. But in the lower region, they swap places. We'll start with the lower region since we're going to go with respect to y. The first integral will go from 0 to 1, and it should be the cubic on the right minus the parabola on the left. Let's copy and paste the equations so we can remember what they are. Setting up the integral now, the first one goes from 0 to 1, and we said the cubic was on the right. That gives me y cubed minus 4y squared plus 3y minus, in parentheses, y squared minus y with respect to the differential dy. The second one should be the second region, which should go between the y value of 1 and the y value of 4. In this one, we said that on the right is the parabola, which is y squared minus y, and on the left is the cubic, y cubed minus 4y squared plus 3y. Both of these are integrated with respect to y. Let's make sure we set them up properly. Is the lower region cubic minus parabola? Yes, it's purple on the right and blue on the left. Is the upper region the parabola minus the cubic? Yes, it should be. Now take a moment and pause the video, work out the definite integrals on your own, then restart the video and compare your answer and your work to mine. Let's see how you did. If you look at these here, make sure that you get the same solutions I got. My final answer came out to be 71 divided by 6. Hopefully you got the same thing. This is the end of this video.